Welcome back. So we are ready for today's lesson on chapter 4. We're going to kind of continue sculpting of the land surface, but this time instead of the running water with the streams, we're going to switch over and look at glaciers and arid or desert type of landscapes. In chapter 4, we'll be focused in on that. We'll start off with the glaciers. The glacier information. And to our glaciers, there are two basic cycles that are in play. One, the hydrologic cycle. If you'll recall from chapter 4, we mentioned the hydrologic cycle. This is the water cycle. So that is that ever kind of movement of water from the ocean. Through evaporation, it goes into the atmosphere. From there, we get clouds and precipitation. It comes back down to the land, and then a couple of things happen to that precipitation. It can either infiltrate or it can run off, but it will eventually make its way back to the ocean, and we say we have completed kind of the cycle. So that's the hydrologic cycle, and the glaciers are part of that. The rock cycle, maybe a little surprising, but yes, our glaciers are part of the rock cycle. Glacial ice. Ice is actually a mineral. As those of you in the geology class, if you've taken that, learned that yes, ice, water ice, is actually considered a natural forming mineral. And in addition, in the rock cycle, glaciers we're going to see really pick up or erode sediment, transport it, and then deposit it elsewhere. So it is very much part of that sedimentary kind of rock cycle in there. And the ice itself, it does sort of recrystallize under all that pressure. And so it's really kind of going through a metamorphosis cycle. So we can say definitely that our glaciers are part of the rock cycle as well as the hydrologic cycle. So glaciers, they are a thick mass of ice. They originate on land though. So any ice that we kind of see out on the ocean floating around, that's called sea ice. The actual glaciers are forming and accumulating up on land surfaces. From the accumulation, the compaction, and then of course the recrystallization of the snow. So I've got here, I'm just going to pop under here, the ice molecular structure, little water ice molecule. And these of course are linking up. You know, here would be another water molecule, right? Six-sided from the hydrogen and the oxygen kind of bonds that are forming. And under heavy compaction, we actually get those to recrystallize from the pressure. It acts just to do a little bit of melting in there and recrystallizing into sort of this solid mass of ice, very thick, solid mass of ice. And I also had a beautiful image of a snowflake from a Physics Today magazine, but you can just see the beautiful array of six-sided pattern coming from that internal crystalline molecular structure from the hydrogen and the oxygen bonding in there. Just a gorgeous snowflake to show you there. But these are thick accumulations, masses of ice that originate out on the land initially. We have a couple types of glaciers that we'll talk about. Now, move this over here. We're thinking about where they're forming, and so the types of glaciers, we have one we call a valley or an alpine type of a glacier, and these are in the high mountainous type of terrain. So they do exist in mountainous areas, so high elevations, and they flow down a valley from the accumulation center at its head. So we can somewhat think of these as when we talked about our streams, how they had a headwaters and they had a mouth, those that were coming from the higher elevations. So we can think of that. We've got an accumulation source at the head of the mountainous terrain, and then of course it flows ever flowing downhill under the influence of gravity, just like our streams did. Glaciers also will flow under the influence of gravity downhill, always flowing that direction. So they will flow down a valley from the accumulation center at its head and continuously move its way down. So mountainous terrain for a valley or an alpine type of a glacier. Now the other type is called an ice sheet, and this is out on more flat-lying continental masses. Sometimes they call them continental ice sheets or glaciers, but they do exist on a larger scale than the valley glaciers. So of these two types, your valley or your alpine glaciers are going to be the smaller of the two. And these ice sheets are huge, the largest of which is in Antarctica. So on the landmass of Antarctica in the southern hemisphere, the South Pole, Antarctica is like the largest ice sheet. But yeah, these are existing much larger scale than our valley glaciers. Two major ice sheets, of course, Greenland is one of them, and the largest one, of course, is located in Antarctica. And sometimes, yes, these ice sheets are called the continental ice sheets, and they will flow out in all directions from one or more snow accumulation centers. And so if you can imagine, say maybe I had a bottle of water and I was going to pour it out on a flat bench, that water is going to spread out in all directions radially. Well, this is also what our glacier, our ice sheet will do as well. It will radially flow out in all directions from that accumulation center. There's a couple other types they mention here. They don't really explain them too much, but little ice caps, these are on just maybe a much smaller scale than our ice sheets are. An outlet glacier is where the mouth of the glacier actually meets up with the sea or the ocean, and they kind of call that an outlet glacier. A Piedmont glacier, so these are coming from the valley or the alpine mountainous terrain glaciers, and once they hit the level land at the base of the mountain, they kind of spread out, and those are known as Piedmont glaciers. And your book kind of describes those a little bit more. So how glaciers move. Okay, we've got a couple types of flow that we talk about. The first one is called a plastic flow. This is internally within the ice itself, a plastic flow. So it's still a solid, but yet it can actually flow. So I always kind of liken it to some warmed maybe candle wax. Not melted candle wax, but that becomes a liquid. But that is still a solid, and you can kind of form it and shape it. So it flows actually, even though it's still a solid. That's what we refer to as a plastic flow. So there's so much pressure because these are very, very thick masses of ice that internally there's enough pressure in there that it will cause the ice to flow. So this is happening within the glacier itself. It's called plastic flow. The basal slip, this happens at the base. So the basal means the base of it. So the entire ice mass is slipping along the ground. So most glaciers are thought to move by this process, the basal slip. Okay. And of course they're always in that movement. They are always going downhill, right? Under the influence of gravity, just like our streams did, just like water does. They're always moving. Okay, so a plastic type of a flow or a basal slip, they call that. These are the types of motion. So zone of fracture. So you get the uppermost maybe 50 meters or say 150 feet. This acts brittle, okay? And you can get fractures in them, and they're called crevasses, okay? That term crevasses, where the upper part of the glacier is acting very brittle, and these can be very dangerous, these crevasses. People can get, trapped down in there, as well as animals, so they can be quite dangerous. In fact, we're still discovering the woolly mammoths, that these animals had gotten trapped down in a crevasse, right? And then of course they got frozen in place there, prehistoric time kind of. And our ice is melting now, and every now and then a block of a beautiful specimen of a woolly mammoth becomes visible over time. I have a picture here of an Iceman mummy, where he was maybe 5,000 years ago, fell into a crevasse, and then they found just a wonderful specimen of him. He's been preserved in the ice, right? Kind of freeze dried, but they've done a lot of studies on him. But yeah, people even can get trapped down in these crevasses, these large fracture zones, where the ice is acting very brittle in these locations. So the tension causes those crevasses to form in that brittle ice. Now, the rates of our glacial movement do kind of vary considerably from place to place, from one glacier to another. So average velocities will vary to where maybe you're not getting anything tens, hundreds, thousands of years of movement, not much, to where maybe you get rates of up to several meters maybe a day. So it will vary quite a bit on what's going on with your glacier. And a lot of that will have to do with the budget of your glacier. So if we think of a budget in our households, right? Money in, money out. We got to make sure everything balances correctly with our checking account kind of thing. So there is a budget of the glacier. And in one zone, we call it the zone of accumulation. This is going to be the area kind of like where the headwaters are for our streams, but the zone of accumulation up there where the glacier is forming. So snow is continuing to accumulate. So your elevation of your snow line can vary greatly as the glacier advances and then appears to retreat, so that snow line can vary, and it'll just go along with whatever is occurring in your glacier. Are you getting an active, accumulation? Or on the other end, are you getting this zone of wastage that they're talking about here? The area where there is a net loss to the glacier. This would be like money out of your checking account instead of money in. So the wastage zone, they also call that the ablation kind of zone, where you're losing some of that glacier due to a net loss to the glacier. And a couple of ways you can get a net loss is melting of your glacier. You'll be losing some of it. That would cause your snow line to recede a bit. Or calving, so actually where the glacier breaks off and calves off. So a lot of times when the glaciers meet up with the ocean or the sea, so of course they're coming from the land, meet up with the interface of the sea, they can calve off and break off into the ocean, and then those floating pieces of the glacier become what we call an iceberg, right? Out where the glacier has met with the sea, or the ocean, reached the sea. That's called calving. Or maybe you're just not getting any accumulation. And so you're losing a net loss to the glacier budget. So there's kind of a balance between accumulation at the upper end of the glacier, okay, and the loss at the lower end. Of course, this is referred to as the glacial budget. Now, if accumulation exceeds the loss, it's going to appear that your glacial front is going to advance. Okay, it's going to look like it's advancing. And if ablation, so here they've introduced that term ablation, which means a loss or a wastage, okay? So if ablation increases, wastage or loss increases, or maybe your accumulation is decreasing, one of those two things, you're getting a loss here, and the ice front will appear to be retreating. Okay, now, I want you to keep firm in mind that the glaciers are always moving downward with the force of gravity, right? Downhill with the force of gravity, but they will appear to retreat, like they're going back up the mountain there. They're not, but it appears that they are because they have a net loss, right, to their glacial budget. There's more wastage than there is accumulation, so it makes it look like the glacier is retreating, but in fact it is always going downward, right, downhill, with the influence of gravity, so keep that in mind. So here's a nice little summary of a few of those terms of the glacial budget. You've got your zone of accumulation there in the upper left-hand corner there. You see various snow lines, how the snow line will change as that glacial budget changes. Here are some of the crevasses where the upper part of the glacier is acting in a brittle manner and can actually fracture, right? Things can get trapped down in there. And then the zone of wastage. So here we are having a net loss to our glacier. And here it's also meeting up with the sea and calving off and forming those little icebergs that will float out in there. Yes, and so that's a nice little picture of all of those terms we looked at. Now our glaciers, so they do a tremendous amount of erosional work, right? Oh, before I get into that, there was a study done, okay, somewhere here, the Rhone Glacier Study. A glaciologist by the name of Agassiz, 1874 is when he began his study. I don't know how well you can see that image from there, but he studied the Rhone Glacier, and so an alpine type of a glacier, and he had put 2 stakes on each side of the valley walls, okay? And he would come back every year, every couple years, and he would monitor the motion of the glacier. And so you can see, maybe you can, maybe you cannot, but there's little lines here, and that's a curved line of each time that he came back to monitor it. And he was noticing that the movement or the flow of the glacier was fastest right down along the center. And this makes really good sense because similar to a stream, if you remember, the stream walls will slow down your stream flow. Out there in the center was where the fastest velocity of our streams were, because that friction due to the contact with the sides of the valley walls were slowing down the flow. And so yeah, from his study he was realizing that the fastest flow or motion was right there at the center. And so he had done a study on the flow of glaciers, and this was in particular the Rhone glacier that he studied. So part of what glaciers do, they erode, they transport, and they deposit sediments. Does that sound familiar? That should sound familiar because that's exactly what our streams did. They erode, they transport the material, and they deposit it. This is what our glaciers do, and our glaciers are capable of tremendous amount of erosion. Very great erosion and sediment transport. The glaciers can actually pick up very, very large boulders and move them on down the line. So they're very capable of great amounts of erosion. So now a couple ways that they do their erosion. This first one here is called plucking. And so it'll actually lift up and pick up the rocks and then carry them along, right? That's one way. Abrasion is the other one. So just kind of scooting along the bottom there, almost acting like a sandpaper, and it can really cause what we call a glacial polish on some of the rocks that we have. Scratches and grooves we call striations can be left behind as a glacier is moving past, because it's picked up all these rocky types of sediment and debris, and then it moves across the bedrock and it will scratch and polish it. I actually have some that do show, some rocks that do show. This one from Ohio, I don't know how well that's going to show up. Looking pretty good from here, but all these scratches on here, those are little striations from glacial motion across the rock there. This one has quite a few of those little striations as well. And the interesting thing about these is that you can tell the direction that the glacier was moving. So my fingers will be going nice and smooth across that direction, but if I take them and I try to go in the opposite kind of direction, you can't feel this, but it's like my fingernails are getting kind of caught as I go on that. It's not nice and smooth like this one was. So you can actually tell the direction that the glaciers were going from these striations. So a lot of studies have been done with that. But striations can get formed by the abrasion as well. And sort of like a glacial polish they talk about. Yeah, so some of these striations, grooves in the bedrock, glacial striations. Rock flour is another one. Really is pulverized rock. Very, very fine, like think of flour. So they do call it a rock flour. Can really abrade, almost like sandpaper, and get a very, very fine powder out of it. It actually do have some of that type of material that I'll show you a little bit later. Glacial kind of rock flour they talk about. I think they have a picture of some striations. There's a bunch of the grooves from the striation. So plucking and abrasion, okay, are some forms of methods of the ways that a glacier will erode, and they do a tremendous amount of erosion. These thick masses of ice barreling across the landscape, right? So we got here a couple of where, first off, they're going to talk about the glacial erosion, some landforms that are created by glacial erosion. And on the other end of this, we'll talk about some depositional landforms. So erosional and depositional, just like we talked about with our streams, erosional landforms from our streams and depositional landforms from our streams. Same thing holds for our glaciers here. So they've listed several things here, erosional features of glaciated valleys, and I think they'll have images of each of these. But hanging valleys. So hanging valleys are, if you think of a mountainous terrain, an alpine type of a valley, and you've got your glaciers coming along, you actually will have ancillary glaciers coming from the side, similar to our tributary streams that fed into our main channel of our main stream channel. Same thing happening with our glaciers. And you'll get some of these tributary glaciers, right, feeding into the main channel of the glacier, and it will erode away the land from there. And so you'll sort of get what we call a hanging valley kind of left behind here. Waterfalls are going to be associated with these hanging valleys quite frequently. Cirques, and so we'll see some of the images here, but cirques are kind of circular, where several of these have met up and created sort of a depression of a circular, almost like an amphitheater looking shape in there. U-shaped valleys, and so we'll be looking at that, versus say a V-shaped valley. Okay, a V-shaped valley is something that we saw with our rivers, right? And then versus say maybe a U-shaped valley. Well, with a river and a stream that we were learning about, those were eroding and cutting downward, right? So downward erosion, right? From the stream, from a stream. if you remember that, those narrow valleys, right? The downward erosion was dominant. Well, here in a glaciated valley, you get a U-shaped valley. Because the snow can pile up, clear up to the sides there, right? So it's not limited to the channel of the stream. It can really come way up here and just barrel through and really cut out that V shape and make it into a U shape. So a U-shaped valley, they call them. It's definitely associated with glaciation coming through and just barreling through and eroding everything, the bottom and the sides of the valley. Fjords end up being where you've got your end of your mouth of your glacier, and it has created a very steep-sided sea. So the sea has inundated that region. After all the glaciers kind of removed, you're left with very steep-walled, deep seaway in through there, a fjord. And a reet, kind of very sharp, jagged ridge formation. Again, where a couple of these glaciers are coming together, they're eroding, and a very sharp, kind of edged ridge will form, and a reet. And a horn, well, if you get several of them, it'll create like a peak out of it, and they call it a horn. And we think of the Matterhorn in Switzerland. That's like a famous glaciated landform of a horn. And I think they're going to give us many of these images here, that which will help. So glaciated topography, where we've got erosion happening here, and then they start here with the unglaciated topography, meaning a V shape. So we had a stream in there causing downward V shape kind of formation, a narrow valley kind of shape to it. Well, if this gets transformed into colder climate, whatever, and creates snow in there, see how it has become more U-shaped now. Here we have, during a maximum glaciation period, the advances of the glaciers, you've got a U-shaped region now. So instead of water, flowing, running water, it is this thick mass of ice now. And so, yes, so when you get several kind of combining, they're showing us the cirques here. They're sort of circular in shape, look like an amphitheater. We've got some of the peaks there, a horn, right? So a nice little peak happening as these are getting carved out. Here's an arete, a nice sharp ridge along there. So several of these little names that they're referring to, an arete, a horn. I know it's probably hard to see from this view, but yeah, our hanging valleys. So you've got a tributary valley coming into your main channel here, and after the glaciation is removed, you can get little waterfalls coming from these hanging valleys. So typically a waterfall is going to be associated with a hanging valley. Okay, there, once the glaciation is kind of passed. Oh, yeah, so there's a bigger image of the V-shaped or the unglaciated topography. There's that word again, topography, shape of the land. Okay, that's a blown up picture of that one before, and maybe they'll give us one of the glaciated one. Here it is. And you can see those terms a little bit better. Okay, during the period of maximum glaciation. Again, these are kind of the tributaries. They're coming in, right? Tributary glaciers coming in and feeding into our main glacier. Think of our streams. They were doing the same sort of thing, right? Yeah, so you see the horn, the arete, the sharp kind of really jagged edge there of the arete, and then a peak from the horn in there, and then the little cirques as well. And they're bringing in some terms here of a moraine, and we'll talk about those here in a little bit, but those are depositional type of features rather than erosional. So once the glacier has melted away, then you're left with these formations, these landforms. The glaciated topography gets left behind there. So the glaciated topography. And so we've got all those little terms, all from erosion again. So the Hanging Valley, right? The waterfall associated with the Hanging Valley. We have probably the most famous and best example of a glaciated U-shaped valley is in Yosemite National Park. You can see the effects of glaciation. So out there in California, if you've been or if you'd like to go, it's Yosemite National Park. That is a glaciated valley, a nice U-shaped valley that you can see. There's the Arits, so we do have some bigger pictures of the Arits. Yeah, the sharp, jagged edge that you're going to get because of the glaciers just carving the landscape. Nice ridge. It's an Arit. Here's a cirque, so it does kind of look like a amphitheater kind of shape, but it's sort of a circular shape in there with the cirque. Here's the Hanging Valley, so associated with the waterfalls. This was a tributary, right, glacier that fed into the main one, but the main one came across and just carved off all of that rock material. And so you're kind of left with a hanging valley, they call it. And yeah, you'll get lots of waterfalls that come through there. Beautiful. Gorgeous, gorgeous landscape. And there's a horn, and you know, that's the example of the Matterhorn, but just a nice peak that gets left behind. Maybe I'll put this one in here. This is the Matterhorn in Switzerland, a glaciated land feature carved out by these enormous glaciers that can do so much erosional work, and just kind of left that peak behind. So that's the Matterhorn in Europe, there in Switzerland. A great example of a horn, a glaciated feature. Famous glacial feature is the Matterhorn. They're in Europe. Here's the fjords. So the fjords, these glacial troughs that have become deep, steep-sided inlets of the sea are called fjords. And yeah, a lot of the cruise, major ships, those cruise ships, they like to get as close as they can, right? So there's the main glacier there. So it's sort of an inlet kind of sea, very steep-sided because it has been carved out by a glacier. And of course the glacier has retreated a bit because it's been melting. But very steep-sided inlets of a sea coming right up to the glacier there. That's a fjord. Again, a glaciated topography. And here's Yosemite Valley. Probably, you know, the one of the best national parks to see these glaciated topography, the glaciated features there. And there's Half Dome right there, where it's a granite dome, right? An exfoliation dome, but the glacier had come right on through there and actually scraped off the half of that dome, and they do call that Half Dome, which is the icon symbol for the North Face clothing company. If any of you have that clothing brand, the North Face, it's named after Half Dome there, which is a glaciated, carved out kind of feature there. They're in Yosemite Valley out there in California. So during times of glaciation, the glaciers did advance that far and did create that topography. So those were all erosional effects of glaciers, okay? So now we want to look at the glacial deposits. So again, glaciers will erode, transport material, and eventually they're going to drop that material out and deposit it. So we'll talk about the various types of glacial deposit features that we can have. So they use this term drift, okay, glacial drift, and it refers, it's like an all-encompassing term that refers to all sediment of glacial origin, okay? But we do kind of separate some of the terms for the types of glacial drift. One here is called glacial till, that first one there. And that is material that gets directly deposited by the glacier. I mean, it just drops it out. So climate changes, the glacier is melting, and that material will just drop out. So it's very unsorted. If you recall, we talked about how the running water of our streams will really sort the sediment by size very, very well, because as velocity slows down, the competence of the stream gets lower and it can't hold a certain size, and so that size will all drop out. Say sand size will all drop out, but it can still suspend the silt size, and so that gets carried a little further away, and then the velocity drops enough and then all the silt will come out. So different sizes, that's very well sorted. Till, on the other hand, here with our glacier is just melting and it's just dropping down whatever it picked up, right, by the plucking or the basal slippage, will drop that out. So you get a mixture, just unsorted mixture, unstratified mixture of various sizes of the till. That's called till. Now, stratified drift, these sediments get laid down as the glacier is melting and the meltwater. So here we get some running water now. Of course, that's going to be very well sorted and layered and stratified. So kind of different there, where you're just dumping it and you're getting the hodgepodge of a variety of sizes, that's your till, versus the stratified that's very well sorted. So a couple types of glacial drift that they talk about, but that general term for all glacial deposits, we kind of call drift in there. That just gets sort of a general term for it. Okay, so the till, here's a little picture of the till. It is unstratified and unsorted, right? You can just see all various sizes of particles in there, even a cobble size there. You can see the scratches on it as well, because yeah, the glacier is going to be scratching along as it goes. That's very typical, those striations in there. But this has just been dropped, right? It rapidly just dropped out. So that's a glacial till there. Okay, the landforms that we can get from the till, we kind of just alluded to it just a little bit ago, the moraines. So the moraines are layers or ridges of till, right? The sediment that drops out. You can get ridges of the material that can build up, just depending on how long the glacier stays in one kind of position, is kind of melting at its front edge, right? It can get a layer of the till to build up. And so here we've got what we see in our alpine glaciers, the moraines. So in the mountainous kind of terrains, we're going to see what we call lateral moraines, medial moraines. So kind of from where they are located. So are they coming along the sides of the valley walls? So those would be called lateral kind of moraines. Or are they going down the center, that ridge of till being deposited down the center? That would be called medial. So lateral off to the sides, medial down the middle. And there's just these layers of till that kind of get built up as you're going, as the glacier is depositing right along the valley, the glacial valley. Okay. Now some other ones that they talk about, an end moraine. An end moraine, kind of how it sounds there, is if we call it, there's two types. One you call the terminal moraine, the terminal end moraine. This is the farthest extent that the glacier went. So it deposited a layer of till, layer of sediment, the farthest extent, okay, that we see that sediment. That's known as the terminal moraine. Recessional moraine, well, we know that our glaciers, the glacial budget, the glacier can advance, the glacier can appear to retreat, right? And so you can get a recessional moraine as well. So one where it went to its farthest advancement, its extent, then times where it had retreated, the glacial budget kind of changed and retreated, you can get what we call a recessional end moraine. And then ground moraine is kind of like intermediate before. It depends on how quickly our glacier was kind of melting and depositing. So you can kind of get an end moraine, farthest extent, then maybe it retreated a bit. And if it was a kind of a quick retreat, right, you can get this sort of leveled off ground moraine in between your terminal and your recessional end moraines. Kind of in between is a ground moraine. So different types of moraines, they say, but these are all just layers or ridges of till that are getting dropped out, deposited by our glacier as it's kind of melting. So here's some of those terms we can get, and they're actually including a few more terms on this figure that we'll talk about. But these moraines kind of things. So, and they're ridges, right? They get left behind. Here would be a terminal moraine. So we get a ridge. This was the farthest advancement of our glacier, which we see back over there. And it left, at one point it got this far out, and it left behind its till right there. Then it receded a little bit. So now here we have a recessional moraine where it laid down another ridge, right, as it was retreating. And in between here, they're calling that the ground moraine. It left behind some sediment kind of as it went along, some of that till. So these are sort of some of the moraines that we talk about. And then some other little features they're going to talk about. Notice here, this esker. An esker is a very sinuous, kind of curving, mounded kind of ridge. But what was happening was there was meltwater beneath, kind of, you know, this was all still icy, but beneath at the base of the glacier, it was actually melting a little bit, and we had some meltwater, glacial meltwater, and of course, water, flowing, running water, likes to meander, right? So you see this sinuous kind of curving and leaving behind of sediment that was brought by that glacial meltwater, and it left behind that ridge we call an esker in there. Some of these are some little cames, little hilltops, little kind of mounds that kind of got left behind, that the sediment sort of dropped out of the bottom of that glacier, and now the glacier has retreated and left these little mounds kind of behind. A drumlin field, these almost look like upside down canoes, and you can really tell the direction that the glacier was moving from the direction of these, but they're kind of just mounds of ridges that looks like an upside down kind of a canoe, but they're called drumlins, and lots of times you'll see them together like a field, a drumlin field, they call that. Little kettle lakes can get left behind. So you had a large maybe block of ice there before, and then sediment kind of went up in and around it, and then later on that ice kind of caused a little depression there, and it got warm enough and that ice melted, and you're left with a little lake, a little kettle lake, they call those. So a little pockmarked with all these different lakes. Oh, and out here they call it an outwash plain, where a lot of that sediment got carried from the glacial meltwater, and it left sort of a little outwash plain, they call it. So many, many features on this depositional features. So this is depositing, it's depositing out sediment. So yeah, they're going to talk about some of these. The drumlins, smooth, elongated, parallel hills here, steep-sided faces. That steep side will face the direction from which the ice advanced, right? The steep side. So you can kind of tell the directions of your glaciers in this manner. And they often do occur in those clusters. They call those a drumlin field. There's a nice one from upstate New York. Yes, this area was glaciated at one time during the Ice Age, we call it. 2-3 million years ago. During that time frame, we had glaciation, periods of glaciation and interglaciation periods. But New York, yeah, was covered by glaciers at one time. So that was a drumlin. Okay, the outwash plains with ice sheet, they're called outwash plains. They're called a valley terrain if we're in the mountainous region. So if it's pretty much a continental flat region where you've got an ice sheet radially going, we call that an outwash plain. If you're in the alpine valley type of glacier, mountainous terrain, they call that a valley terrain. So that when in a valley. But broad, ramp-like surface composed of the stratified drift deposited by the meltwater that's leaving your glacier. So of course, water, running water, the meltwater, is going to very well sort that material. So they call it stratified kind of drift from the meltwater. Located adjacent to the downstream edge of most end moraines. So you saw that ridge of the end moraine, and then that outwash kind of plain was after the farthest advance of the glacier. And often pockmarked with the kettle, those little kettle lakes. And I've got a little diagram of how that kettle lake gets formed in there. So your glacier's coming along, and then it begins to retreat a little bit, right? And it leaves behind the ice, and then that outwash kind of covers it with sediment. And then over time, you get a depression there because that block of ice was so heavy, and it gets covered with some sediment, and then the ice melts. And so you're left with a little, looks like a pot or a kettle, they say. So they call it a little kettle lake in there. So nice little depiction on how those are forming. So these are some of those glacial deposit landforms. And they included some more there, the ice contact deposits, so deposited by the meltwater that's flowing over and within at the base of motionless ice. And so the cames, right, the little hilltops that the material just deposited out from the base. And then the eskers, that meltwater that's actually going along, sinuous, kind of curved, and leaving sediment all along the way, but in that curvy, sinuous motion there, the eskers get left behind. Okay. So glaciers of the past, and so kind of our most recent kind of ice age that we've had, where ice actually covered 30% of the land area. It began, like I mentioned, 2 to 3 million years ago. Okay, most of the major glacial episodes occurred during that division of time. This is the geologic time scale that we call the Pleistocene epoch. So maybe write that down. The Pleistocene epoch is when our latest kind of ice age or glaciation episodes kind of occurred in there. The Pleistocene epoch, and this is part of the geologic time scale. Rather recent events, right? 2 to 3 million years ago. Geologically speaking, was not all that long ago, but it did. It covered about 30% of Earth's land surface. Glaciers did. Here's a little image of just how far the glaciers did go. So the maximum extent of the glaciers during the ice age, those 2 to 3 million years, where we had advances and retreats and advances and retreats. So, you know, it kind of went back and forth in there. But this would have been the maximum extent of the ice. And so noticing here, here's the United States down here. I don't know how you can see that. But the glaciers never came as far as Arkansas. It did kind of midway up into Missouri. Yeah, they did make it that far, but never made it quite down here to Arkansas. Although we do have some remnant features that I've already mentioned last time about Crowley's Ridge, if you remember that very fine rock flour material of sediment that was glaciated and then got windblown. So we'll talk a little more about that with our windblown deposit features when we talk about our deserts. But it actually came from the pulverizing and just grinding of those glaciers, the work of the glaciers, powdered up that sediment. But this is sort of the extent, maximum extent that we had during the Ice Age, those 2 to 3 million years time frame of the Pleistocene epoch. And there are some indirect effects of the glaciers of the past. So this would have kind of forced the migration of animals and of course plants, and it did. Even just here in North America, we used to have the woolly mammoth, the mastodon, the saber-toothed tigers, the dire wolves. They went extinct, right? So they either had to go through land bridges. Some were able to migrate because when glaciers were covering, that actually made a land barrier from, say, Alaska on over to Russia. There was a land barrier there because of the glaciation. So they had to migrate or become extinct if they could not adapt to their new climate. So yeah, these glaciers forced migrations of animals and plants. It could change stream courses. We already mentioned in chapter 4 how the Mississippi River has changed courses, right? The Arkansas River has changed courses. So when you get all of that mass of ice on the land, it's actually going to bow down the land a little bit, right? And then when the glaciers recede or melt, it's going to rebound a little bit. So the path that the rivers and the streams are going to go can change over time. So we did kind of see some of that, even just with our Mississippi River that we talked quite a bit about. But changes in stream courses. Here's the rebounding upward of the crust from the former centers of the ice accumulation. So there was so much mass and weight from the thick ice blocks that did bow down, and then now they melted, so you start to get this little rebounding upward of the crust that happens. Worldwide change in sea level. So let's imagine here, let's say that all the glaciers on our planet melted today. We would actually see a rise of sea level by 300 feet. That could spell trouble, even here in Monticello, Arkansas, because that elevation, a lot of our elevation is about 300, maybe a little over 300 here in Monticello. But some of our lower lying area, you know, our neighbors to the east of us, that's that Mississippi River floodplain, right? They're in a much lower elevation. They would be inundated by water. So yeah, if all the glacial ice did melt, we would see sea level rise about 300 feet. So when we did have glaciers, as you could imagine, when we had that maximum amount of glaciers, well, how are we getting those glaciers on the land? The water from the ocean is evaporating, right? It's going up into the atmosphere, and then it was cold enough that it precipitated as snow, and that snow accumulated and stayed on the land, right? So that water from the ocean was coming up onto the land and staying frozen. It wasn't making its way back to the ocean, right? It was frozen on the land. Not very quickly, it didn't come back to the ocean. So that would have lowered our sea level quite a bit. And in fact, Florida, if we think of the peninsula of Florida, it actually used to have a much wider diameter because sea level was down, right? So yes, worldwide change in sea level definitely does and can occur because of the glaciers or the melting of the glaciers. So definitely. And climatic changes as well. So if you have cooler climate, right, you can have a little bit less evaporation happening. So this can really change up many various scenarios for your climate. So definitely have undergone many different kind of climate changes. And they do say we are in, you know, a climate change right now. We're globally warming. And in fact, it's at an alarming rate to where they do believe humans. It's a human-induced warming type of a scenario. that's happening now. Okay, so switching from the cold deserts or the glaciers, we're going to move over here to deserts. Although deserts don't necessarily have to be hot, they can be cold. And in fact, Antarctica, which is our largest glacier, is also our largest desert. So what is a desert? A desert is basically a region that gets less than 10 inches of rainfall or precipitation a year. So yeah, you're thinking, well, there's all this ice in Antarctica. How could that be? You know, it doesn't get, it gets less than 10 inches of an equivalent of rainfall per year. But whatever does fall there stays there, right? So it accumulates and accumulates. But yeah, it's actually our largest desert is Antarctica. But that's a cold desert. We do think of a lot of them as being hot deserts, but the main thing of a desert is the amount of precipitation. So there's definitely a deficit of moisture there. So dry regions cover 30% of Earth's land surface. So we do have some major belts where we have deserts, regions located. Distribution and causes of dry lands, and so very important here. We've got two different types of climate zones, and they typically kind of surround one another. But a desert or an arid region, again, that's less than 10 inches of precipitation a year. It is like the textbook definition of a desert, less than 10 inches of precipitation or rainfall or less a year is a desert. Now a steppe pretty much surrounds the desert regions, like a transition kind of zone, but a steppe is kind of semi-arid, and those locations get about less than 20 inches of rainfall per year. So it's a semi-arid region, and usually you'll see those surrounding your desert regions. Okay, where we're finding them. Okay, and I think I might have mentioned this and probably showed you something back in chapter 3 when we were talking about the hydrologic kind of cycle and talking about how water is not evenly distributed across the planet. So yes, they've got a nice one there. Hopefully it's pretty well color coded. I got another one that's really color coded, but we'll try this one out here for this one. The desert and the steppe regions of the world. And so the major desert regions of the world are located at 20 to 30 degrees north and south latitude. So here's our equator, right? There's the equator. And then I don't know how well you'll see it, but we've got latitude going this way. Here's 20, here's 30, here's 40 north latitude. Here's 20, 30, 40 degrees south latitude. And so in that little belt, okay, that little zone, 20 to 30 degrees north latitude, 20 to 30 degrees south latitude, we have a region where there is sinking air that ends up compressionally warming the air, and so it ends up drying up all your clouds, and so the amount of precipitation becomes very, very low in that region. And we will talk more about the atmospheric circulation when we get to the atmosphere part of the semester, but it needs to be talked about here. These are known as the subtropic regions. And again, it's color coded here, the yellows and the browns, right? Going right along a strip there. 20 to 30 degrees north or south of the equator. Here again, color coded in the yellows and the browns. Sort of a strip right across there and a strip right across there. Those are the major deserts of the world, regions of the world. And they're known that is known as a subtropical high pressure system, and that is causing sinking air, and sinking air will compress and warm, and that dries up any chance of clouds and precipitation in there. So that zone of air pressure called the subtropics, main region of the deserts of the world. We also do see some deserts in some mid-latitude regions. So but they're towards the interiors of the continent. So we have here in the United States sort of a major mid-continent kind of a desert happening, the desert Southwest we talk about here. But you can get some of those, and those are really due to the terrain that you have. You have some mountainous terrain and your atmospheric airflow playing together, and we'll talk about that in a second, on how it's forming at the interiors of the continents like that. So that first one, the subtropics, make yourself a note that the major deserts of the world are in that zone of the subtropics, which is about 20 to 30 degrees north and south of the equator. There's a high pressure zone, circulation zone in the atmosphere there. So these are what we would call low latitude deserts because they're, 20, 30 degrees north-south latitude. They call that low latitude deserts. They are under areas of high pressure and sinking air. So the air is sinking. When the air sinks, it compresses and it warms. Compressional warming, we call that. And we'll learn more about this, but it doesn't hurt to interject it in here because it's coming. But it's affecting us now here when we're talking about deserts. So compressional warming, high pressure zones called the subtropics. That's why we're seeing it, just straddling the equator like that. In those zones, in those atmospheric belt zones, they kind of call them. So the major deserts are right along there, very well explained by the atmospheric circulation in those locations. The other ones we talk about are the mid-latitudes. These are located in the interiors of the continents. They're pretty much far away from any ocean kind of source, so they're not coastal kind of regions. They're in the interiors of our continents. High mountains, so the terrain, the topography plays a big part in this. But when you get some sort of a barrier, a mountain barrier that blocks the atmospheric flow. So here we have a scenario, let's say, on the west coast of the United States. We've got the Pacific Ocean out there, and the prevailing atmospheric wind circulation is bringing that in from the west and starting to come across the United States. Well, it gets imposed by several mountain terrains along the way, right? The California, we've got the Sierra Nevada mountain ranges out there, and that wind, the prevailing wind, will be forced to rise, okay? As it hits the mountain range in the path, it's going to be forced to rise. When air rises, we will learn, it expands and it cools to the point that it will condense water. And that water will condense, form clouds, and then those clouds will all rain out on the windward side of the mountain range. Well, the rest of that air comes over the mountain and it sinks. What did we just learn about sinking air? Sinking air will compress and warm. When it does that, it dries up all the clouds and it creates what we call a rain shadow desert on the leeward side of the mountain range. And so this is what we do see out there, our desert Southwest. We also see this in the Midwest states, kind of like Kansas, Nebraska, and along in through there because of the Colorado Rocky Mountains, right? It's going to be forcing that air to rise, an orographic lift, we call that, and then it comes back down on the leeward side of the mountain, very, very dry. So we do call that a rain shadow desert. So that's another good explanation of where we're seeing our deserts in the interiors of continents. And so topography, the terrain, the mountainous terrain. Oh, here's a beautiful pictorial of the rain shadow desert. And again, this is off to the west coast of the United States, starting over here with the Coast Range, mountain range there. You can see how it's coming along, and it really, the Sierra Nevada mountain range is a very imposing mountain range, and it will go up the side. It'll be forced to rise. The air will be forced to rise, and you can see that we've got clouds forming on that side. It will rain out on that side, on the windward side of the mountain, and it will come over and descend down the leeward side of the mountain right? The leeward side becomes very dry. This would be the Great Basin region. And we see that scenario played out again with the Rocky Mountains as well. So we've got several kind of imposing mountain ranges, these barriers that block that atmospheric circulation, causing our rain shadow deserts. We'll talk more about rain shadow deserts when we talk about the atmosphere, when we get to that. So our deserts. And it might be counterintuitive to think about the role of water, right, in a desert, but water, like we said, running water is that single most important erosional agent of sculpting of the land. So the role of water in arid climates, most stream beds are dry most of the time. However, they do get, 10 inches at least by definition, but deluges. I mean, it doesn't come sporadically. When it rains, right? So, they're dry most of the time, but when they get them, they're going to get it, just a deluge of water. So what we call our desert streams, they're called ephemeral. So that they're dry most of the time, but they'll carry water when they get the rain, right? Only during the periods of the rainfall that they get the water. So that's called ephemeral. Pretty much dry all the time until the water comes. But different regions will call them different names, and so you don't really have to remember all these different names. But a wash, an arroyo, a wadi, right? Some different names that we call the streams, desert streams in there. But they're ephemeral. They're only carrying water during the times of the rainfall. Most of the time they're going to be dry. And they're continuing the names here depending on the different regions. Donga for South America and Nola for India. But desert rainfall, the rain often occurs in these heavy showers and deluges. I mean, it's not the sporadic kind of spaced around kind of thing. You're going to get a deluge of water. Okay, you really do have to pay attention because this can, result in flash flooding. So all of a sudden, it seems like a beautiful blue sky day, but off away in the mountains, it might be raining, and then all that water's making its way to the desert region there, and you can get some deluges. And flash flooding is really, really, a problem. But that rainfall is going to cause some erosion during that time, right? Problems that we see because of the flash kind of flooding out in our deserts are any vegetation that we have is very sparse, so it's spaced really far apart because what those plants are doing, their root systems are really spread out beneath the earth's surface there. They're trying to take advantage of whatever moisture comes their way, so they're sparsely kind of spread out, first of all, so the vegetation is sparse. And that runoff is unhindered because remember how the roots of plants would kind of help to bind the soil? Well, here they're so sparsely, spaced that the water is just going to run unhindered. And so flash flooding is very common. You get poorly integrated drainage systems. And so streams lack extensive systems of tributaries, so it kind of has no way to get back out from the terrain there. So most of the erosional work in a desert is done, strangely enough, by running water. Most of that erosional work is done by running water. Okay, even though it's infrequent, that is where most of the erosional work does get done, by the running water. Might seem strange to think about that for our desert situation, but that is the case. Oh, here is a picture of a dry channel off on the left picture, and then all of a sudden it just fills up, right? So if someone was, kind of making their campsite out here thinking, oh, that's a dry bed, haven't seen water in a long time, this should be a good spot. Then lo and behold, here comes a flash flood, and your campsite would be down the river there because this is how it happens. It comes up really all of a sudden, a flash flooding type of a situation. Can be quite dangerous. Okay, basin and range, evolution of a desert landscape. So when we talk about the basin and range region on sort of the western part of the United States, I've brought some demo, my little fault block demo here. This is just representing layers of the earth, land. And so what's happening out there, the uplift of mountains and block faulting, we have on the land, kind of out towards our west, tension. So there's sort of a pulling apart of the land. And when I pull apart, you get a drop down block. So a fault block that happens. So you get higher terrain and then this one here, the down drop or the fault block terrain. So you get what we call horsts and grabens. The higher elevations are called horsts and the lower ones are called grabens. Okay, so you just kind of see this repeat one after the other, a basin and a range. So the range is kind of the higher elevation and those lower graben parts are the basins. Okay, so basin and range, evolution of a desert type of a landscape. So it's characterized by interior drainage. The landscape evolution in the basin and the range region. So we've got an uplift of some mountain blocks by block faulting, so those faults drop down block and an upper blocks. The interior drainage into the basin part, so the low part. And once that water kind of comes down in there from the ranges, the water comes down, it gets in the basin and I mean it can't get back out, right? Other than evaporation that happens. That's about the only way it can come out. So the interior drainage goes into the basins and it will produce some of these kind of depositional features that we talk about, alluvial fans. And they do kind of look like fans, but alluvial, that term means coming from a stream or a river, right? We learned that, the alluvial floodplain, right? Well, this is an alluvial fan. So it's coming down from the range or the mountainous region and it hits a more flat-lying region and it will fan out. All that sediment will kind of fan out, and so they call it an alluvial fan, right there. That is called an alluvial fan, kind of a cone of sediment at the base of the range at the basin, okay? An alluvial fan. They call it a bahada, so you can actually get several of these alluvial fans side by side. Well, if they merge with one another, so like an alluvial fan here, an alluvial fan here, and they're meeting. Okay, and they're merging. We call that bahada. Okay, the playas and the playa lakes. So, like I mentioned, the water will get down there in the basin, and it can create these very shallow lakes, these little pools of water. The playa lakes, they call them. And of course, the only way that water's getting out is through evaporation. Can't go back up the mountain range, right? So it gets down in there and it kind of stays until it evaporates kind of out. So we have our basin and range landscape. And in fact, you know, Death Valley is down in one of those basins. So it's a drop down, it's a very low region, and that's a desert. That's just like the hottest, iconic kind of desert that we have, and that's in a basin, right? The basin and the range, very arid kind of region there in our basin and our range. So the landscape evolution of the basin and the range region over time, right? If you continue to get the ongoing erosion of your ranges or your mountains, you're eroding those down. Well, all the while you're filling in your basins. And so eventually, it's saying produces sediment that fills the basin, and this will diminish the local relief. What they mean by relief is the gradient. So the highest elevation to the lowest elevation is called the relief. Well, you're diminishing that. As you're eroding the mountains, all that material is building up in the basin, and eventually you're going to level that out. So yeah, ongoing erosion of the mountain mass is going to act to diminish the local relief in there. That sediment's going to fill in your basin. And of course, we're talking a tremendous amount of time for this to occur, but geologically speaking, this will occur. Produces isolated erosional remnants called Inselbergs. So these look just like, almost like they're an erratic little knob of rock, a big boulder of a rock, and it's just sitting out there on an otherwise very flat terrain. So what is happening, these little erosional resistant rocks get left behind as the rest of the material eroded away. And so these are called sort of isolated erosional remnants called Inselbergs. I think they've got a little picture of them. We do see quite a few of these out in Southern California, that Basin and Range region, out towards Southern California, right? The Basin and Range region. Some Inselbergs, and I don't know if any of you have seen the movie Tremors. I'm talking about the 1990 version of Tremors, but these were the rocks that the townspeople were, trying to get away from the creature from and stay up on those rocks, to be safe from the creature down below the ground. Yeah, I don't know if you've seen that movie or not, a little classic sci-fi. But the Inselbergs were the rocks that they were standing on. But very common, Southern California, right, where they do a lot of movies out there. But Tremors was part of that. Might help you remember Inselbergs, but kind of an erosional remnant from that. Yeah, so eventually you're going to get sort of the land flattening out over time. So that was all kind of work of water, believe it or not, in our deserts. So now we want to look at wind erosion, and wind will pick up some sediment, but it can't be very heavy. Maybe sand size, it can pick up a few feet and then it drops. It picks up a few feet and drops. So it can kind of move sand size, but of course dust size, right, silty sized sediments can be picked up by the wind, and I mean really carried great distances, because after all, the atmosphere doesn't have any channels like water kind of stays in a stream channel, but the atmosphere has no boundaries. So when the dust, whatever, is picked up by the wind can carry it, hundreds of thousands of miles. So we think of the Saharan desert, making it all the way over to South America. So that atmospheric circulation, it doesn't really have a boundary. So transportation of wind, it can be a tremendous amount, but the particle size is very small. So it does differ from the running water in those couple ways. So the wind is less capable of picking up very coarse material and transporting it. Has to be the dust size or maybe sand, it can lift it a little ways. And wind is not confined to the channels like a river is, and it can spread sediment over very, very large areas. So wind erosion, yeah, we'll talk about a couple of those. Wind erosion. Now how it's going to transport that sediment, okay? Some of these terms might look similar to the stream transportation methods and processes. So one called a bed load. Remember, we had that process with our streams where it was scooting things along the bottom of the channel. Well, mechanisms of transport here, the bed load. Saltation, skipping and kind of hopping and saltating, rolling, kind of skipping and bouncing along the surface. That's part of the bed load. Particles larger than sand are usually not transported by wind. You may get a huge gust that could lift something, a little heavier, but typically it's not going to transport particles larger than sand, at least not very far away. Okay, so that would be kind of a bed load, saltation or somersaulting along, skipping along the surface. And suspended load. So suspended load, it's carrying it up in the atmosphere quite a ways up and large distances and covering a large area from that. So suspended load. Okay, and you can definitely have some problems with this transport of the sediment from the wind. Back in the 1930s, we had the Dust Bowl, and I think your book may show an image of that. I've got something here as well. But yeah, during the 1930s, sort of wind erosion produced an area in the western parts of Oklahoma and Kansas, so kind of in our Midwestern kind of states in there. Real problem with the Dust Bowl, and we call that. Here's a bunch of sediment that is just coating. It looks like a vehicle right there, and here looks like the wagon wheels, farm kind of equipment that they had there. I mean, it just covered everything. It was really, really hazardous time, and a lot of people had to leave because, you know, of course, their crops and their lands were devastated by this. So that was during the 1930s and the Dust Bowl. So lots of problems with wind erosion can happen. So this can be quite problematic in there. So mechanisms of transport, actual lifting up with a loose kind of material in there, that's called deflation. And it can produce these little blowouts, right? So wind or deflation, shallow depressions called blowouts, and desert pavement over time can be created from this deflation. So you can get the wind bringing up the small little particles in between the larger ones, right? It's not going to lift the larger ones or the cobbles kind of thing, but all the little sandy material in between, right? And then it can really create over time what we call desert pavement. Quite beautiful, almost like you would want to build it for yourself, but it's done by wind erosion. A surface of coarse pebbles and cobbles, right? All the little stuff has already been wind blown away. And so it creates sort of a desert pavement, they say. And wind, of course, is relatively insignificant, of course, to the erosional work that running water does, right? When you compare it to running water, it's relatively insignificant. But we can get some features from deflation. Of course, I don't think they're going to talk about it in here, but closer to kind of home here in Arkansas, we do have some little features that we call prairie mounds that are produced by deflation. We have these, we actually have these here in Monticello, over by the Drew Central kind of campus. If you look off out into the tree area, there's a bunch of pine there. You'll see these little mounds, right? And that was produced by a wind-blown kind of a deposition sort of feature, that deflation feature. Oh, here's the picture here where deflation, the wind is kind of picking up the smaller sediment, right? Continues to remove the final particles, and then here you're left with all larger cobbles and pebbles. That's called desert pavement. So it's kind of a formation of the desert pavement. But yeah, that deflation is what has produced what we call little prairie mounds here in Arkansas. There are a bunch of them in Hamburg. So here's Hamburg on our little map there, a little south of Monticello there. Hamburg has a lot of these as well. Little mounds, right? I think over by their school they had them. A lot of times you'll have a tree in there kind of anchoring some of that sediment. But these are some wind-blown kind of mounds that we get. So produced by deflation, picking up a fine sediment and then depositing it elsewhere. So that, what we call prairie mounds, is produced there, you know, the Hamburg kind of area, the result of deflation, called prairie mounds, kind of a cute name. But think of the prairie mounds when you think of that deflation out there in Hamburg. Yeah, so some significant kind of depositional landforms are created by the wind in some areas, when we've got our little prairie mounds. But here we've got a couple of wind deposits are the dunes, okay? A sand dune, right? For example, mounds are ridges of sand, and they're often asymmetrically shaped. I think I got a picture of this, of some terminology here. But asymmetrically shaped. So the windward slope is kind of gently inclined, right? And then you get a drop off. The air velocity kind of changes and you get a drop off. And so on the leeward side of the slope, it's called the slip face. Right? It's a little steeper slope there. So here we got wind coming along, right? It's picking up the small particles, saltating grains. Remember saltation, the bouncing and the skipping of the sand grains. So the wind's coming this direction. That's a pretty steep slope there, right? On the windward side. Here's the leeward side. So leeward is opposite of the windward side. And it's a little bit steeper kind of a slope there. It's called the slip face. And notice that term, the angle of repose, right? The different size particles will have a particular angle of stability, right? The angle of repose. This is the slip face, and that's on the leeward side. So the leeward side is the opposite side of the windward from the direction that the wind's coming. That's the windward side, and then the slip face is on the leeward side. And so this is sort of what you'll see in a sand dune. They'll look like that. Okay. So yes, you're going to see the leeward slope is called the slip face of our sand dune. Okay. And here's some sand dunes in the western United States. Very lovely picture there. Or if I have any others. I have one here. I think it's coming from a postcard maybe. It's beautiful. Oh, I actually have some of these. Have some of the pink sands here. Here's the pink coral sands. I mean, it's kind of a pinkish color from Utah. And this is the beautiful, beautiful picture. But you can see the little sand dunes, kind of that beautiful pinky color. They call it coral color. And yeah, so you're getting the gentle slope, the windward side, and then the slip face of your sand dunes. So that's kind of a postcard type picture. Out there in the sand dunes out there in Utah. Gorgeous photo there. Western United States, yep. We're getting our sand dunes out in that region. These are depositional features from wind deposits. Another type here that we've mentioned before, but officially talking about it here, is loess. So L-O-E-S-S, it kind of has a loess pronunciation. It's a German word that means loose, and it is loose little sediments, but very, very fine grained. So silt, they call that. So blankets of wind-blown silt, okay, very fine grain, much more fine than a sand, okay. I brought some loess. Two primary sources they talk about, but here's some loess from Crowley's Ridge, and it's just very fine grained, right? Very soft, powdery, that rock flour we talked about. And the loess that we had here in Arkansas, it built up Crowley's Ridge. If you remember, I spoke of Crowley's Ridge before. So they're talking about two primary sources for loess, this windblown deposit. One is a glacial outwash deposit. So glacial action, erosion has really just pretty much abraded by abrasion, turned that sediment into rock flour. So very, very fine silt. And then the wind picked it up and deposited it, right? Remember, the glaciers did not make it down here to Arkansas. However, the wind-blown silty deposits did get blown here, and that built up that ridge, right? Crowley's Ridge, if you remember that. It built up Crowley's Ridge, and that's that sort of natural divide that we have as a geographic province here in Arkansas, Crowley's Ridge. That's a Loess deposit, right, that we have here. Also have some in Vicksburg, Mississippi as well. Let me grab that picture. You might be familiar with this area, but some very thick Loess deposits near Vicksburg, Mississippi. If you drive by, you might see these cliffs of this just very thick, fine-grained sediment. This is the Loess deposits that we have that got windblown, right? Again, Vicksburg, Mississippi here. This is Crowley's Ridge on the left here in Arkansas. So Loess deposits here. And these were from glacial origination of those sediments, right? And then got windblown. The other ones they talk about here are coming from, sources are from deserts, of course. And so we would see large deposits of this. Oh, where's my deserts of the world? Yeah, here it is. China. So China has extensive Loess deposits because of the Gobi Desert there, right? It has the Gobi Desert. So here, you know, these are the deserts of the world sort of thing. And out here in China, Gobi Desert, and that region there, all that wind-blown materials coming from the desert is the origin or the source in China. So western and northern China, that's where the most extensive Loess deposits are located, right? Extensive, the most extensive, is located in China, we would see. And of course we've got some here, central United States as well. But the thickest and the most extensive Loess deposits are occurring in the western and northmost part of China, okay, northern part of China. Okay, but yeah, we can see them here a little closer to home, central United States. We even got it here in Arkansas, and we do have it in Vicksburg, Mississippi as well. You can see them in the road cuts there. Okay, so that actually does conclude chapter 4. So we've looked at more erosional and depositional work, sculpting of the land by glaciers and by deserts. And so that will bring us then to chapter 9. We're going to skip ahead to chapters 9 and 10, where we're going to focus in on the ocean, the working and the mechanics of the ocean. So I will see you next time. All right, thanks.